Hi, we have seen that Lipschitz functions on Euclidean spaces have the surprising property that they have a derivative almost everywhere. That was the famous Rademacher's theorem that we proved, or actually just discussed its proof earlier in the videos. Based on that theorem and another deep result due to Whitney, it is true, in fact, that Lipschitz functions coincide with C1 functions on arbitrarily large parts of their domains. The precise statement is written here, and we're going to talk about its subtleties and its proof here. In future videos, we will use this fact to give a second proof of the area formula. So I'm going to include all of these videos in the same playlist as the previous area formula material. Okay, so the result is quite surprising, and it just shows how nice Lipschitz functions are. In fact, due to this, we can, there is this, informally, what we conclude from this is that any, I want to say integration because that has to do with measures more intimately, result that is true for C1 maps is also true for Lipschitz maps. Of course, we cannot give a precise statement of such a general claim. The idea is that, first notice that the result above is stated for R1 target, but if you apply it to coordinate functions, you can deduce the same for maps from Rn into Rm. So to prove something for Lipschitz maps, say you want to prove area formula, and this is something we will do. Or you want to prove co-area formula, for example. At some point, I will also talk about co-area formulas. Excuse me. Or implicit function theorem. With the right interpretation, there is, excuse me, I'm suffering from a cold. So implicit function theorem, with the right interpretation, also holds true for Lipschitz maps. So examples of the things you can prove using this informal argument are these, and the way we prove them is we look at the nice part of our sets where the map coincides with C1 and you get the result you want from the smooth case. The remaining part has small measure, and then you use some exhaustion argument, some measure theoretical tricks to get rid of that set in totality. And that will be our approach to the area formula, to the second proof of area formula within a couple videos from this one on. Okay, so as I promised, this video will be about just the subtleties of the theorem and how it is proved. Okay, so let's begin with the typical example of a Lipschitz map, or function rather, here, and that is the map of y equal absolute value of x. So if we try to draw a picture verifying how the theorem claims the existence of C1 approximation, we call that result a C1 approximation, although it's not an approximation, it's coincidence on a set. So we approximate a set rather than the function. So something like that. So this blue function coincides with it everywhere, except for a tiny interval containing that singularity. And this we can make as small as we want. So A very natural question seeing the result above is that what happens if I take a sequence of epsilons and I let them go to 0? Because when you get a bigger part of the domain where things are nice, like this one, so if you make the epsilon smaller, then you get a smooth map, another smooth map, which coincides with the function now on an even larger set. So what can I just not repeat this process and get rid of all those bad parts except for a null set? Can I reduce everything down to a null set? The answer is no. There does not exist one unique C1 function from R to R that coincides with this absolute value function on R minus 0. Because derivative must be continuous to be C1. However, we see that on the positive side of the x-axis, derivative is +1, and before that it's -1. You cannot be extremely close because you then make a jump from -1 to +1. We will come back to this again later. What you can get, though, is the following. That you can exhaust your domain, so you can find a null set and then some countable union of measurable sets such that, okay, so n is null, and for every I natural numbers, there exists some C1 function such that f coincides with gi and its derivative coincides with the derivative of gi on ei. So this is what you get from the exhaustion, really, just taking bigger and bigger sets. But again, the point is that you don't get one unique C1 function, but rather a sequence of functions. So in reality, this is no stronger than what we had with 1 epsilon. Okay, you can also say that this is saying that my function f is C1 outside the null set n. But if you try to write a precise statement, what does it mean to be C1 outside the null set n? What does it mean for a function to be C1 outside, say, a countable and dense subset? The best you get is just what is written down here as the corollary. Okay, so to see more, let's do the following. So we can say that, okay, we can combine E1 and E2 in this example, this claim. And because G1 and G2 agree on the overlap, because both agree with f, say we just connect them and make them one function. So that G2 is now defined on E1 union E2, and G3 similarly will be defined on E1 union E2 union E3. So then you get a sequence of functions defined on larger and larger domains, and each time on that domain they agree with f. Does that not give us some stronger result? The answer again is no, because of the following observation. The limit of a sequence of C1 maps or functions need not be C1. And this is not at all surprising given that we have a similar situation with continuous functions. So limit of continuous functions, even nice ones like monotone and compactly supported and things like that, need not be continuous. And a picture that is relevant to previous example that I had in mind is this one. So you are approximating, so you have your functions in the sequence are functions of this type. So you go this way and then this way. So this is your f1. Your next function does the same, but it does it closer to the origin. Something like that. And then you get the sequence that is similar shape, but this going through the origin happens later and later each time. The limit of such a function, such a sequence of functions, will be you have, say, -1 before 0, 0 at 0, and then +1 in the positive direction. So the limit of this becomes the discontinuous function 1 for positive x, 0 at x equals 0, and -1 at for values negative. So limit of this continuous and each one monotone sequence of functions becomes a discontinuous functions. And this is exactly, if you integrate these functions, what you get is the failure of this C1 approximation to be holding everywhere. The derivative, so you can think about the discontinuous function as being the derivative of the absolute value of x function. Okay, so you can imagine, ignore the value at 0, and you can imagine that this is the derivative of this function. And antiderivatives of the colored functions are approximations of that. So, for example, blue might be something like this, and then smoothing out, having a 0 derivative, and then entering negative region, and then again becoming constant slopes, something like that. And the red does this kind of later. So not the best pictures I could get, but you get the idea. So here we have some C1 functions whose limit becomes this absolute value x function, which is not C1 unless you cut out a neighborhood of 0. And this is exactly because their derivatives in the limit fail to be continuous. So you should look at these diagrams going downward. Okay, so that's these examples I hope convince you that the C1 approximation result that we had is already kind of sharp. And in regards to how big of a nice part of the domain you can get, this is the best possible. Okay, so now that we have looked at some intricacies of the claim and the very statement of the theorem, let's look a little bit into its proof. So we want to say that a Lipschitz function is as nice as a C1 function on a large part of its domain. But let's see why are C1 functions nicer in the first place? I mean, what is it about C1 functions that we like, or that makes them smoother compared to Lipschitz functions. So the first thing, of course, is that let's compare them to Lipschitz functions. Okay, C1 functions have derivative everywhere. And this derivative is actually continuous. So Rademacher says that they have derivative, the Lipschitz functions, almost everywhere. So they're not much worse in that regard. X going to the derivative of f at x is continuous for C1 maps. For this, we discussed in the context of proving area formula that this is measurable. Okay, so how weaker is this compared to continuity? Due to this Lusin's theorem from measure theory, if we sacrifice a set of measure less than epsilon positive arbitrary, then it does become continuous. So that's toward improving the Lipschitz functions. So Lusin kind of bails out the failure to be continuous necessarily. Okay. The other thing we have is that, and this follows from Taylor's theorem, with remainder, you must have some precise estimate for the remainder, gives us the following. If f is C1, then writing the Taylor expansion of f around x, so to estimate f of y, we can start off with f of x, put gradient derivative of f dot y minus x, this is dot product of two vectors, plus the remainder, which depends on y and x, obviously. Then, okay, so then f is always equal to this, where the remainder, the whole point is about the remainder, that ryx is little o of y minus x, but I want to avoid that terminology and just say, even if I divide this by y minus x, then this converges to 0 as y minus x goes to 0. And the most important part to us will be that this is uniformly in x from any compact set K of Rn. Okay, so there's something here we have to decipher, and that is, okay, so this going to 0 as y minus x goes to 0 is that this will be less than epsilon, provided that this is less than delta. But this could depend on the locality, the neighborhood where y and x live, and that delta could fail to be uniform over the whole Rn. But what is this saying is that if you fix a compact domain of Rn, and for x and y required to be in this compact set, then there is a uniform delta which doesn't depend on x and y. So that means x can be moving around and y can be moving around. As long as their distance is small, this ratio of the remainder over y minus x will go to 0. So that is the uniformity we're talking about here. And why this is true for C1 maps again follows from the at least one particular form of the remainder theorem. And the compact part guarantees that the partials of f are bounded, and there is an upper bound on how big they can be. For example, if f was C2, the remainder is in terms of the second derivative of f. And if you are in a compact set, you know that that second derivative has a bound. You will be good. Okay, so this is only for C1 maps. Can Lipschitz maps compete here as well? Okay, so what do we know about f that is just Lipschitz? Then, okay, by Rademacher, and also let's say that we have actually sacrificed this small set. So then above reductions, or rather sacrifices, say that derivative of f at x is continuous. So at this point we have already discarded a set of epsilon measure. And at every x, by definition of derivative, fy minus f of x minus derivative of f at x applied to y minus x divided by y minus x goes to 0 as y converges to x. Let's say y minus x goes to 0. So, but this is at every x. So for every x, there is this convergence. It's very, very far away from being uniform or anything. So what we do then is that given k inside our n compact, we define the following quantity. So notice that this is actually ryx, this remainder, divided by y minus x. Okay, and notice that our goal is to show that this converges uniformly on k as y minus x goes to 0. So let's look at the worst case. So let's say how bad the worst that this can get for y and x from k, and y minus k smaller than, say, 1 over j. So we want to set delta to 1 over j and see what is the worst that can happen. And the hope is that for j large enough so that 1 over j, this delta is small enough, we will have all of these small. So this, let's call this some function phi j, now evaluated at x. So here, sorry, we freeze x already. So this is like, okay, phi j at x. So for every x, this is defined, and then you can, so this gives a sequence of functions, phi1, phi2, and etc. So what we know from above, from this pointwise convergence, is that phi j of x converge to 0 as j goes to infinity. That means the functions phi j converge to 0 pointwise on this part of the domain where the derivative exists and also is continuous. Now here comes another important theorem from measure 3, and that is Igorovs Theorem. What Igorovs Theorem says, maybe not exactly the version that you may have seen, but an immediate corollary of that gives us that if you have a pointwise convergence, after sacrificing a part of your set, your domain, you get uniform convergence on compact sets. But so here you can say we have Rn, some small sets removed, so we sacrifice another set of measure less than or equal epsilon, so that now phi j uniformly converges to 0 on compact subsets. So here, implicitly, I'm assuming that this changes, this K, the compact set, is not just one fixed one. You could say, well, we fix a compact set and we find this, and then you can pick a bigger compact set and find this, and then you take some diagonal argument or something. What is true, though, is that Igorovs theorem says that this convergence to 0 can happen uniformly on compact sets, and that is exactly the condition that we had for the C1 maps. So even in that regard, after sacrificing a small set, we can have everything working. So the result, the summary of all of this comparison. We have derivative also after sacrificing a set. We have continuous derivative after sacrificing a set. We have some uniform convergences from Taylor's theorem for C1 maps. We get similar ones after sacrificing some little bit more set and applying Igorovs theorem. So summary, after sacrificing, so with sacrifice, of course, I'm just saying removing a set of measure at most epsilon, 2 epsilon, which will be the same as saying epsilon, from Rn. We have that derivative of f is continuous, and f of y minus f of x minus derivative applied to y minus x divided by y minus x converges to 0 as y minus x goes to 0 uniformly on compact subsets. Okay. Now comes the biggest and deepest result that we need, and that is Whitney's extension theorem. So the version we need here is kind of the one of the easiest variants. So Whitney's extension theorem, it's from 1934, amazingly, is kind of true for all order derivatives in arbitrary dimensions. What it says, and I'm again boiling it down so I get specifically what we need here. So this summary is saying that on that part of my domain, f behaves like a C1 function. If f was going to be C1, we would have to have these conditions: this convergence uniformly on compact sets, and of course the derivative is continuous. So f does behave as if it was a C1. What Whitney's extension theorem says is that if f together with a vector valued function say V. So these are, so let me be a little bit more precise here. Okay, if C subset of Rn is closed, we can get closedness from, after sacrificing these sets of epsilon, we can sacrifice a little bit and assume that the set is, the set we have is actually closed. So just another, maybe we would sacrifice 2 epsilon, sacrifice 3 epsilon, so that you can enlarge the exceptional set to an open set. And once you remove the open set, the complement is closed. Anyway, so if C is closed in Rn, and if f from C into R is a real valued function, together with a vector valued function from, again, the C into Rn, so at every x it gives you a vector, satisfy so are continuous. So if these two functions are continuous and satisfy that f of y minus f of x minus this v at x dot y minus x divided by y minus x goes to 0 as y minus x goes to 0. So here y and x are both from your set C, and uniformly on compact subsets, then the Whitney extension theorem says that actually V and V can be the gradient of a C1 function. So this V is not a coincidental vector field, it's actually the gradient of a C1 map, which agrees with F. So then there exists a map G from Rn into R that is C1, and okay, g of x equals f of x for every x in C, and gradient of g at x equals this v of x for every x in C. Okay, so that's a baby with an extension theorem. Going back to what we had accomplished, you can regard this, so on a subset C closed, we have got that this is continuous. With that, I mean, again, gradient. And this is my Vx, and I have this necessary condition satisfied in the Whitney extension theorem. And so the conclusion of the Whitney extension theorem gives me the C1 function that I was looking for. That means there is a C1 function that agrees with F on this large set C, and its derivative, that means derivative of G, agrees with derivative of F on C again. And that ends the proof of the C1 approximation theorem at the very beginning of the slides. The proof of this Whitney extension theorem is not at all easy, and it's one of the most amazing results in analysis. Going back over this proof, so this was maybe the deepest result we used. Rademacher's theorem shouldn't be taken for granted. That was another deep result, and remember, everything started off with that. The other two theorems, Igorovs Theorem and Lusin's theorem that we used, are kind of the basic tools in measure theory. So they weren't really here that deep. They were just tools that we applied. So C1 approximation result mainly depends on Rademacher's theorem and Whitney's extension result. Okay, so as I said, we will be referring to the C1 approximation result in future many times. In particular, within the next two videos, we will give a proof of the area formula using the C1 approximation and some basic stuff from manifold theory. So if you have any questions, please put them in the comments. The reference I used was again Evans and Gary Epe's book, Measure Theory and Fine Properties of Functions. And here exactly we see a fine property of functions. A Lipschitz function is finer and nicer than we think. It agrees with the C1 function. So, aptly named book. Until then, have a great time. See you soon.